All right. Hello, hello, hello. So on to our next lesson here in what are we doing? We're doing rates of change. Yay! So well, let's see. Unit 2B is kind of our extension of the derivatives unit. So we're kind of doing some extra stuff. We've already learned exponentials and logs and inverse tan. We learned all those derivatives. So we're getting pretty good at our derivative shortcut rules. Now we're going to bump it up a little bit, starting getting a little bit more application. So today, tomorrow, the day after, they're all dealing with applications of derivatives, of rates of change. Okay. So today might seem a little bit more like review because we've touched on a lot of this stuff already as we've done stuff with derivatives and talking about velocity and stuff. All right. So you got a little warm up here. Welcome to try that on your own, and we will get after it in class. Just a little reminder to help you off with number 1 to get you started and not confuse you. The variable in this problem is x. Everything else, those are constants. So all those numbers are constants. Keep that in mind as you try that problem. Okay. All right. So rates of change, physics types problems. You've probably done problems like this in your physics class. Maybe even done a derivative without realizing it. But anyway. S, which is S of t or F of t, we already know that this is the position function, and that the velocity is just the derivative of that, okay, which we call v of t. We know that. We've done this already. One thing I've kind of held off on is speed a little bit. So speed can be found by taking the absolute value of velocity. So, I mean, this is nothing more than the absolute value of v of t. Which this is equal to the absolute value of s prime of t. Okay. So I mean, you know, it's the same as finding the velocity, but if it's negative, you just take the absolute value of it. It's really the same thing. It's just that speed doesn't have a direction associated with it. Velocity does. All right. We know that acceleration, which is a of t, we know that's equal to the derivative of v of t. And we know that that is also equal to the second derivative of s of t. Okay, so if I take the second derivative of s of t, I'm at a of t. If I take the first derivative of v of t, I'm at a of t. That's the relationship. Okay. We also know that objects at rest only when v of t is equal to 0. That has nothing to do with acceleration. Okay, it's when our velocity is at 0, or when our rate of change is 0, we're technically at rest. And most of the time, this happens at like extrema. So like maxes and mins and stuff like that. Okay. And one other thing that we have not talked about, something to add to the list, is that we can find distance. All right. So I'm going to label this as total distance. By doing the absolute value of s of t. And I'm going to describe that further and why it's absolute value here in a little bit. Because if we don't do absolute value, technically what we're finding is something called not distance, but displacement. And you'll see the difference as we go along in the problem. So displacement is like the change in position. Okay, it's not the total distance you've traveled, but it's how, like, the difference from where you started to where you ended. I mean, think about distance. I mean, think about going on a trail, like a hiking trail or something. I don't know. I'm trying to think of a good example here. Like, look, let's say like we're curious about the total distance we've traveled from bottom to top of a mountain, maybe. Well, when you're going up a mountain, maybe you have to make detours. You have to go down and back up, down and around somewhere up. You know, you're having to go all over the place, right, to finally get up a mountain. So let's say that this little image I just drew is literally us like climbing a mountain range. So here's where we start, here's where we end. The displacement is just that total, like the starting point subtracted from the ending point. It's the comparison of where we start. Like we start at 0 feet and we end up at an elevation of 1,000 feet. That's our total displacement. Now, the total distance is all that moving around, going forward and backwards until we're finally there. So total distance will always be greater than your displacement, because of all that back and forth that we're having to do. And we'll show an example mathematically of that in a little bit. All right, some stuff I've written down a bunch of times before, and you can rewrite this down just to help us out. Just different problems that show up. So when objects are moving, v of t has a direction associated with it. Okay, so when an object's moving, in the context of the problem, sometimes we're talking about a particle moving right and left. Sometimes we're talking about a ball going up and down. Sometimes we're talking about a car moving forward or going backwards. Whatever the context is of the problem, if v of t is greater than 0, if it's positive, then this is the positive directions associated with it: forward, right, and up, or up, not and, but usually or. If velocity is negative, the directions associated with that could be that we're going backwards, it could be that we're going left, it could be that we're going down. And when velocity is equal to 0, that just simply means we're at rest. We're not moving any direction. We are momentarily not moving. And we talked about what it means to be speeding up and slowing down. So speeding up is dealing with both acceleration and velocity. It's when they have the same sign, when they're working together. If velocity is moving forward and acceleration is moving forward, like if they're both helping each other out, they're speeding up. They're speeding up in the positive direction, I should say, like forward. Now, if they're both negative, like so if velocity is negative and acceleration is negative, it means we're moving backwards, but we're moving backwards in an increasing rate. We're speeding up backwards. Just something I wanted to clarify there. And slowing down happens whenever we have opposite signs. So like v of t is positive, a of t is negative. That means we're moving forward, but we're moving forward slowing down. Okay, so positively moving forward, but a negative acceleration means we're slowing down. They're working against each other. Now, if v of t is negative, we're moving backwards, but the acceleration is working against us, so we're slowing down. We're moving backwards at a slower rate. Okay. I don't know if you can hear my dang birds, but I can. I'm shutting this door. Stupid birds. Okay, let's try some examples. So maybe, let's see, I got 3 of them, I believe. Or actually just 2 of them. I might just do one. This might be a shorter video shoot. I might do both of them. We'll see. Gives us more time to work in class. Okie doke. So the position of a particle moving back and forth. So here's a perfect example. This is called a particle in motion. All right. This is actually the name of the chapter. Particle in motion. A particle likes to move back and forth. It's a sciencey thing. Okay. The position of a particle moving back and forth in a straight line is given by the equation. Boopity boopity boo. Where t is the time in seconds and f is in meters. So like at any given time, it's telling me where this particle is positioned at. That it's forward at this position, it's backwards at this position, whatever. Now you can graph this, and we'll graph this in a little bit, but you can see what's going on here. Anyway, just make sure in these problems that we pay close attention to the units because they love to count off for not putting units down. All right. Anyway, this right here, this is the position. F of t, this is my position. Okay. Velocity at any time t is just the derivative of that. So v of t, which is nothing more than the derivative of f of t, or s of t in some cases, is equal to 3t squared minus 12t plus 9. Okay. Power rule. We know how to take the derivative, nothing too crazy about that. Part B, what's the velocity at 2 seconds? 4 seconds. Well, again, nothing crazy about that. Just plug 2 in and just plug 4 in. Should be all right. 3 times 2 squared minus 12 times 2 plus 9. What did I get? -3. And the units, meters per second. So precisely at that time, at 2 seconds, we are moving backwards, all right, -3 meters per second. That's what that means, okay? And v of 4 equals, let's see, 3 times 4 squared minus 12 times 4 plus 9. And I got 9 meters per second. So that means precisely at that time, so at 4 seconds, the particle is moving 9 meters in the positive direction, so to the right, 9 meters per second. Okay, I'm going to come back to this graph. I'd like to show y'all what's going on here. I really want us to visualize this stuff today. All right, so talking about a particle motion, we'll start off at time equals 0. So I'm going to look at this part of the graph. And my original equation was t cubed, thank you Forbes, t cubed minus 6t squared. Oh, and it doesn't like t, so I got to use x. I forgot about that. So x cubed minus 6x squared, and then plus 9x. All right, so look what happened. This is modeling what's happening as my particle is moving left to right, or as my particle is moving. So given any time. So starting at time 0, as I move forward, oh, it won't let me move a dot. I thought I was allowed to move a dot. It's going to bother me now. 0, 0. Oh well, I thought I could move a dot. Anyway, what's happening here is that the particle, as time is moving forward, oh, there we go. As time is moving forward, my particle is moving in the right direction. And then after time equals 1, we're moving in the negative direction. We're moving backwards. So like this, so this models when we're moving to the right, and then this is modeling when we're moving to the left. And then after it looks like time 3, we're moving to the right again. So this models where my function or where my particle's at any given time. So forward, backwards, forward. Now, what we just found was the velocity at time equals 2. So time equals 2 is right here. Okay, notice how it's a negative velocity. So, and we found the answer to be -3. That means that at this precise time, we are moving backwards 3 meters per second. At 4, we found the slope to be 9. That means we are moving at a rate of 9 meters per second. Do we see that? Do we kind of see how that's working there? What that means in the context of the problem? Let's keep going. So again, this is my position function. What is the speed at time equals 2? Okay, well, we know now that speed just equals the absolute value of v of t. So what is the absolute value of v of 2 in this case? Well, v of 2 we found was -3 in the previous problem, and that's just equal to 3. So speed is the same thing as velocity, just without the direction. It just means, hey, we're moving 3 meters per second. Which direction? I don't care. That's speed. Okay, it's a different type of value. All right. What is the particle at rest? So if I ask that question, we know that v of t must equal 0. I hate when my thing does that. V of t equals 0. That's all it's asking. So the particle is at, so a lot of times I'll ask for justification. So let's practice that right now. If I ever ask when a particle is at rest and I say why, what if I ask the question why? The justification is real easy. All you got to say is a particle is at rest when v of t equals 0. So that's, you just pretty much got to restate it. You got to say, hey, this particle is at rest when v of t equals 0. That's your justification. And then you just solve for it. So in this case, we know that v of t was what? It was 3t squared minus 12t plus 9. We're going to set that equal to 0. And we can solve that quadratic all day long. Let's divide everything by 3 to help us out at the beginning. And we got t squared minus 4t plus 3 equals 0. And I think this factors just beautifully. T minus 3, t minus 1, t equals 3, t equals 1. So it's at time 3 and time 1 when we are technically considered at rest. We're going to look at the graph at that in a second. So when is the particle moving forward? Again, the justification is it's moving forward when v of t is greater than 0. Let's get in the habit of really explaining our y's here. Why is the particle moving forward? It's because the velocity is positive. All right. So where does this happen at? Well, I know that I'm at rest. So if you can find your points at which you're at rest, finding when you're moving forward and moving backwards is really easy. Like, we're starting off at time 0. Here's time 1. Here's time 3. Okay. I mean, think about, like, if I want to know where it's moving forward, it's just where my velocity is positive. So if this up here is my velocity equation, t minus 3 and t minus 1, let's test some points in there, see where it's positive, where it's negative. Like if I plug 2 into that, it's going to be a negative times a positive, which is negative. If I plug, say, like a half into that, it's a negative times a negative, which is a positive. And if I plug any number greater than 3, it's going to be a positive times a positive, which is a positive. So think about, like, I mean, think about what the derivative of this function was. It was, think about, I mean, it's 3t squared minus 12t plus 9. I mean, if I had to graph this, it probably looks something like this. So that's the graph of v of t right there. And you can see it's negative between 1 and 3, and positive to the left of 1, and positive to the right of 3. Okay. So when is this particle moving forward? Here and here. So I'm going to say the time is between 0 to 1, and from 3 just on to infinity. Okay. Now let's look at the original graph. Look, when is it moving forward? It's moving forward from 0 all the way up until we hit 1 second. Then it's moving backwards because the velocity is negative. Then we hit at 3 seconds, we start to change our direction and we start to move forward, move in the right direction. Now look at those points we're at rest. It's at 1, 4 and at 3, 0. The reason we're at rest there is because that's a change in direction. Whenever we change in direction, there's a momentary pause in us moving. All right. If we're moving right, in order to move left, we have to momentarily pause to change directions. Those are moments we're at rest, when the slope is 0, when the horizontal tangent is 0. Okay. So all good stuff to keep in mind. Okie dokie. Let's keep going. Find the total distance traveled during the first 5 seconds. Okay. Let's talk about this. Now, let's look at the graph. The first 5 seconds. Let's pull up 5 real quick. 5 is, where's the point 5 at? Man, 5's all the way up there. Okay, well, I don't want to zoom up too much, but 5's off the charts. Okay. So keep this graph in mind. If I were to graph this, I'm gonna just kind of pull this graph over here for us so we can see what's going on. All right, this is 0 to 5. Okay, we know at the point 1 that it changes directions, and then at the point 3 it also changes directions. We found that in a previous problem. Okay, now total distance. The total distance is me adding up all the time, like adding up all these values, traveling along this line, adding up our total distance traveled. Okay. Now, it's not simply taking the position at 5 and the position at 0 and just taking the difference. So like, oh, hey, we're all the way over here. This is where we started. This is where we ended. So that's the total distance we traveled. No. Doing that is the total displacement. It tells us the difference in where we started and where we began. That's total displacement. Total distance is adding up how much we went forward, adding up we went backwards, adding up all the time we went forward. Okay. Now, how we do this is pretty simple. It's just the absolute value of S of t. And the reason that we're doing the absolute value of S of t is because we want to account for this backwards movement of us going in the negative direction. If I didn't account for that, it would counteract this positive and it would just cancel it out. We got to account for moving backwards. So the absolute value is going to take away that negative distance traveled and make it positive to account for all the total distance traveled. All right, it's a pretty simple process to this. We want to add up like the intervals on which we're moving forward, the intervals on which we're moving backwards, all that stuff. So here, I'll do it right here. What this looks like is I want to do like the distance traveled from 0 to 1. And then add the distance traveled from 1 to 3, and then add the distance traveled from 3 to 5. We're breaking up where we're moving forward and backwards. We're going to do our forward, and then we're going to add how much we went backwards, and then add how much we went forward. Okay. And how we do that is we just take the difference between the two. So for instance, this one right here is the absolute value of S of 1 minus S of 0. And that's going to tell me the distance that I traveled, all right, from time equals 0 to time equals 1. And then plus the difference between S of 3 and S of 1. And, you know, again, if I didn't do the absolute value, that number is going to be negative. It's going to be a negative distance, and that would end up taking away from my distance. That would give me the displacement. I can't do that. Okay. And then plus the absolute value of S of 5 minus S of 3. Now, adding these three distances together, they'll tell me the total distance traveled. Okay. So, like, okay, what are my positions at these points? So this will be like, so let's see, S of 1 is 4, S of 0 is 0. S of 3 is also 0, and S of 1 is we found to be 4. And plus S of 5 was pretty high up there. It was actually 20. And S of 3 was, again, 0. Okay. Now, you see why I put the absolute values here. If I didn't, that would be 4 plus -4. That total like change in distance would counteract each other and would give us the wrong answer. We traveled 4 in the positive direction. We traveled 4 in the negative direction. And then we traveled 20 more in the positive direction for a total distance traveled of 28 meters. Again, you cannot just do S of 5 minus S of 0 because that would not take into account the negative distance traveled. All right. So hopefully that made a little bit of sense there. Just break it up into the intervals on which it's moving forward and negative, and then just add up the positive numbers. Okay, let's keep going. So find the acceleration at time t and also at time equals 4 seconds. So we know the acceleration is the derivative of velocity. All right. So a of t is equal to the derivative of, it was what, 3t squared minus 12t plus 9, I think it was. So the derivative would then be 6t minus 12. So that's just the power rule. Okay. Now, if I wanted to know it at, say, time equals 4, a of 4 equals, and then it was 6 times 4 minus 12, which equals 12. And the units of measurements in this case is 12 meters per second, or meters per second squared. It's this rate of change and the rate of change. That's meters per second per second. All right. So that wasn't too bad. Now, let's do these last two, and then I'll save the last problem for our notes tomorrow. H says, when is the particle speeding up and when is it slowing down? So the justification here, and I'll it's pretty simple. It's exactly how we teach it. The particle speeds up when the signs are the same. So we'll justify it as particle speeds up when V of t and A of t are both positive or negative. Slows down when V of t and A of t are opposite signs. Okay, so there's your justification. Not too bad. So let's draw a number line to help me figure this out. It's not too terrible. We already found part of this in a previous problem. We already found out when V of t is positive. It occurs at 1 and 3. Remember, it went positive, negative, positive. Okay. Now, for A of t, which is in part G here, we got to figure out where that is equal to 0 to figure out the intervals where it's positive or negative. So we set that equal to 0. And we get that t equals 2. So right dab in the middle. Now, if I plug in like maybe 1, I end up getting a negative number, so these intervals are negative. If I plug in like 3 or 4, the interval is positive. So where they're the same signs is where they're speeding up. So speeding up, the same signs occur between 1 and 2, as well as 3 to infinity. That's when we're speeding up. And we're slowing down whenever we have opposite signs. So that would be like 0 to 1 and from 2 to 3. Okay. And honestly, we might be able to see that on our graph. So where we're speeding up between 1 and 2. So like between 1, wait, oh no, sorry. Yeah, no, we're slowing down between 0 and 1. So 0 to 1 is like we're kind of slowing down. And then when I get to 2 right here, I start to speed up. And as soon as I hit 3, wait, I'm looking at the wrong interval. Okay, so sorry. We're slowing down from 0 to 1. There we go. I'm sitting there. Okay. Come on. There we go. From 0 all the way up to 1, we're slowing down. Okay. And then from 1 to 2, it's like we're going down here, like we're speeding up. All right. From 2 to 3, we begin to kind of slow down. And then from 3 on, we speed up again. Okay. We're going to discuss more about speeding up and slowing down in terms of a graph at a later time. All right, I'm at 28 minutes. I got one question left. Let's get it done before the 30-minute mark. We'll be set. Draw a diagram to represent the motion of the particle. Oh, this isn't bad. This is just a conceptual problem to help us understand it. Draw a diagram to represent the motion of the particle. A particle is moving left to right, so we're going to draw a horizontal line to represent left to right. And we're going to represent like the distance, like 0, and the farthest we ever go is like 20 after 5 seconds. So here's what's happening. The particle is moving to the right, and it goes this way all the way up for like maybe 1 second. Okay, we found this earlier. We found S of 0 to be 0. We found S of 1 to be equal to 4. And then what happens is, I'm going to draw it above it a little bit so we're not overlapping. The particle shoots back to the left. We found the distance after 3 seconds to be going backwards 4. So it went forward 4, and then it went backwards 4. And then after time equals 3, again, I'll draw it above it so there's no overlap. It shoots to the right and continues to the right forevermore. Okay, because we ended up finding S of 5 to be 20, but it still goes on forever. Okay. All right. We'll clarify any questions on this video later. I got only a few seconds left before I reach my 30-minute cutoff, and we'll do the last problem tomorrow in class. So good job, guys. Y'all are awesome as usual, and y'all have a great day.